Problem number 5 is another problem where we have parallel conducting plates. And in this question, it's asking for the direction of the electric field. Again, we can see that we have positive charges on the top plate and negative charges on the bottom plate. And the electric field goes from positive to negative, out the positive into negative. So in this scenario, the electric field is going to go down. For part B, what's the magnitude of the electric field between plates? So in this scenario, we need to figure out what's given to determine how we're going to solve for the electric field. We have voltage, which is 100 volts. We have radius between the plates is 0.01 meters. We have the mass of the oil drop, which is 4.8 times 10 to the negative 16 kilograms. And then we have gravity, which is 10. Okay, so in order to determine the electric field, we have the equation E is equal to KQ over R squared. We don't know Q, but we do know that voltage is equal to KQ over R. Let me do lowercase r there. And that we can plug the equation for Q, if we isolate that, which is VR over K, into the equation for electric fields. I'm going to plug in VR over K in for Q. That simplifies the equation quite a bit. And we can see that the K's cancel out and one of the R's cancel out. So then V over R is going to equal 100 volts over 0.01. And that gives us 10,000 newtons per coulomb for our electric field. So the next step is what's the sign of magnitude of the electric charge on the oil drop when it stays stationary? So the key here is that it's stationary. My oil drop, and they gave us a clue because they mentioned gravity, is going to have a force of gravity pulling down. And in order for it to stay stationary, it needs a force pulling it up. And in this scenario, since we're in an electric field, we know that we need to have an electric force pointing up. And in order for that to happen, we need to have an attractive force between the charge and the positive. And so that would cause this charge to be negative. It always, negative charges always oppose the direction of the electric field. So in this scenario, the sign would be negative. And then the magnitude would be a sum of the forces equation. We know that we've got a force of gravity pulling down. Generally, I think of downward as a negative direction. And even though the electric force is attracting the positive charge, if we make it a negative charge, then it would create a negative force. But when we're doing some of the forces, we want to think about the direction. And in this case, it's moving upward, which I'm going to define as the positive direction. So here, my sum of the forces, it's the electric force minus the gravitational force. That should be balanced, so equal 0. And therefore, I've got KQ little q over r squared is equal to mass times gravity. We want to find the magnitude of the electric charge. And so in this scenario, we're going to isolate the q. So I've got mgr squared over kq. And I can now plug in my values. So here, I have a mass of 4.8 times 10 to the negative 16. Gravity is 10. The radius is 0.01 squared. K is 9 times 10 to the 9th. And then Q I can get from my V R over K. And actually, if I put that in here, I can simplify a bunch of things. So if I plugged in V R over K, I notice that, and I know I have number values and variables, but I've got the K here, cancel out with that K there. The radius here, cancel out with one of the radii here. And I actually end up with Q is equal to 4.8 times 10 to the negative 16th times 10 for gravity, 0.01 for the radius, and a voltage of 100. And when I plug that in, I end up with 4.8 times 10 to the negative 19 coulombs. And I already stated that the charge is negative, so I'm going to add a negative there, and that's going to be the charge of my oil. For part D, we now have the mass reduced, and because the mass is reducing, we no longer have balanced forces, so we're going to use the same sum of the forces equation. So the electric force minus the gravitational force is now equal to MA, and so we've got KQ over R squared minus MG is equal to MA. And then we are going to make our substitutions. So again, I'm going to right off the bat substitute my equation for Q, which is right here, because I know that'll simplify a bunch of things. So I'm going to take K little q over R squared and multiply that by this right here, which is my big charge, VR over K. And then I know that a bunch of stuff can reduce. And then I still have to subtract my mg and divide it by mass. So that's equal to acceleration. Simplify this, gives me VQ over, I'm going to distribute the denominator, so it'll be MR minus G is equal to A, and that gives me 100. My charge is going to stay the same, so I'm going to take my charge from C, and I'll just use the magnitude of it because the sign does not factor in into any of the calculations. Just tells us it's an electron. And then the mass was reduced to 3.2 times 10 to the negative 16. The radius is 0.01, and then I'm going to subtract 10 for gravity. One thing to note is that just because the oil drop has reduced in mass does not mean that the charge is reduced. Mass and charge are not related at all, so the charge stays the same as the oil drop evaporates. So let me calculate the acceleration, and I end up with an acceleration of 5 meters per second squared. And that is your final answer for problem number 5.